As we continue our discussion about the use of the law of signs, we're now to a point where we are going to talk about the ambiguous case of using the law of signs. And that ambiguous case, I apologize, I'm going to read this to you. We won't remember the idea of angle, angle, side, or angle, side, angle, or side, side, angle. What we need to remember is that to use the law of signs, we need an angle and the side opposite that angle and one more item, either another side or another angle. That's what we need to remember. And we also need to remember that when we're dealing with the law of signs, we just use two of the ratios as an equation. Although we've got three ratios in the law of signs, we use two of them. And when we use two of them, of course, like you see here that I've got listed, side A over sine of angle A is equal to side B over sine of angle B. We use the law of signs to find one piece of information, so that means we needed the other three. And so anyway, at this point, what we did in the previous lecture, what I showed you were examples where we use the law of signs to calculate the length of a side. So we were either given two angles, and one of them was opposite a side we already knew, or we calculated, we were given two angles and calculated a third side whose opposite, a third angle whose opposite side we knew. What we have not done is use the law of signs to calculate an angle. In other words, we've never used the law of signs where we were given two sides and one angle opposite one of those sides and calculate the angle, and the way we'd calculate the angle is we have the sine of A. So this case is called side-side angle. See that, for instance, in this case, side, well, put it this way, side, angle. So we would have these two pieces and this piece, but we wouldn't have angle B, and so we'd have to calculate angle B as an example. Anyway, when we use the law of signs to compute an angle, as in the side-side angle case that I'm describing here, unexpected results may occur. This is called the ambiguous case. Well, the ambiguous case in the two, it's actually more examples, and I'm just repeating what I already said. When we're using the law of signs to calculate an angle, if two sides and one opposite angle are given, there are three possibility situations. That we may get the fact that there's no triangle that exists that has those two sides and that one angle. Or there may be a unique triangle, one single triangle that exists that has those two sides and that one angle. Or there actually may be two distinct triangles that have those two sides and that angle. And that's why this is called the ambiguous case. In the cases before, we had one triangle that satisfied the conditions given. When we were given two angles and a side, we had a single solution. In this case, when we're given a side, two sides and an angle, then we may not have a solution. There may be exactly one triangle, there may be exactly two triangles. And so it obviously presents problems when we're dealing with these. Well, let's look at what it may look like when we're doing a problem and see how these issues arise. Okay, so in this example, and we don't know this in advance, let's make sure I'm labeling it this way, but in this example, we're going to have a single solution to this triangle. We're solving the triangle. We're given angle A is 42 degrees. We're given side A is 22 inches and side B is 12 inches. And so this is that case where we have side-side angle. Okay, it's a case like that. And so what we're going to have to do is to calculate two angles and one side. Now, if we can calculate one angle, then the other angle is easy to calculate because the sum of the angles has to be 180 degrees. And the law of sines seems to apply here because we have an angle and a side that's opposite it. We know that. And we have a second side, so we could calculate the angle opposite of it. That's what the law of sines would allow us to do. Whoops. Now, I just made a point here, and that's all it is, just for us to remember later on. A triangle can have no more than one obtuse angle. It might not have any, but in this case, if there is an obtuse angle, it's not angle B, is it? Because side B is smaller than side A, and angle A is 42 degrees, so side B has to be less than that. And my diagram makes it look that way, but that's one of the reasons I could draw my diagram this way, because I knew that information. Okay. Well, where are we? Remember, what we've got to do is we've got to come up with angle B, we've got to come up with angle C, and we've got to come up with side C. That's what we've got to do. And I'm choosing to find angle B first because of what I just described. I know an angle and the side opposite it. I know the side that is opposite of B, and so that seems like the law of sines is right here ready for us to pick from. And so I'm using the idea in the law of sines that side A divided by sine of A is equal to side B divided by sine of B. But I actually chose, if you will, and that's this form, A over sine A, B over sine B. But I'm choosing instead to use the reciprocal form of those ratios. And I'm putting what I'm looking for on the left side. And so I'm looking for angle B. So sine B over B is equal to sine A over A. That's the form I'm going to use. And the reason I'm going to use that form is I can take this equation and multiply both sides by side B. And so I'll have a way to calculate the sine of angle B. And once I know the sine of angle B, I ought to be able to determine the value of B itself. So sine of B is equal to B times this fraction, sine of A over A. And the significance, again, is I know that side B is 12 inches, and I know angle A is 42 degrees, and I know side A is 22 inches. And so from that information, I've calculated that the sine of B is equal to, angle B is equal to 0.364980 Now, I don't really need to do this calculation, but I've done it just to give you some information to look at. And if I'm going to do this well, I'm saying I don't need to do this calculation right now, but if I'm going to use this calculation later on, then I need to have a lot of decimal places so my accuracy stays reasonable. Now, to continue then, what I need to do is to find angle B. And this is an important concept that we'll come up with later on. Of course, to find the angle B, I've got to use the inverse sine key. That is B is the inverse sine of this number. See, that would mean the sine of B is equal to this number, and that's what I'm trying to find. So B is the inverse sine of this number. Now let's keep in mind, of course, that the inverse sine function always gives a result between negative 90 degrees. We usually say pi over 2, don't we? Negative 90 degrees and positive 90 degrees, and certainly this is in that range. Now, I need to also point out, like I started to say, that from our original problem, we know that angle B is smaller than angle A because of the relationship of the sides. And so that means we know angle B has to be an acute angle, and so the inverse sine function calculated that properly for us. It is an acute angle. Okay, and that's kind of, we knew it couldn't be obtuse. And the reason I'm worried about that is there's two angles, 21.4 degrees, and another angle that is, what would it be, about 158.6 degrees. Both have the sine 0.36498803. But since the other one's obtuse, it couldn't be the right one. We know we're acute. I'm rambling here, but I hope that you're getting a little bit of the gist of what I'm saying. The other thing that I mentioned, that I show below this, is I didn't really need to do this calculation and get this decimal. I could have just put the sine of B is equal to this expression, so B is the inverse sine of this expression, and then I would have gotten rid of some of the round off error. But nevertheless, I know that B is approximately 21.4 degrees now. And remember, I'm trying to find B, C, angle C, and side C. So where does that put me? Well, because of our information previously, okay, let's remember that we already knew angle A, we already knew side A, and we knew side B. And what we needed to do is to calculate angle B, angle C, and side C. Now, since I know angle B and I know angle A, then I don't need anything special to calculate angle C, do I? C would just be 180 degrees minus angle A minus angle B. The total has to be 180. And when I do that, I get 116 degrees. So now I know angle B, angle C. The only piece of information left is side C. Now, here becomes the question. If I'm going to calculate side C, I need to use probably the law of sines again. Okay? And this time I'm using it of this form. And when I use the law of sines, I want to use as much actual information as I know. So I'm using the law of sines in this form. Side C over sine of angle C is equal to side A over sine of angle A. I know angle C. I know side A, I know angle A, I'm looking for side C. That's the reason I've chosen to do this. And so as I put these pieces in, okay, that I know, then all I'm going to do is take this resulting equation and solve for C by multiplying both sides by this denominator. And that's what I've shown here, of course. And I get C is approximately 29.4 inches. Well, then that finishes off the problem. I have all the pieces of information I need, and that's what I was to do. So I have one unique solution, one triangle that has all of these components that satisfied the first three pieces of information that we were given. Okay, let's move to the next problem. And it's a little different. Now this is announcing, and let me remind you that when we're doing this work, it's not going to say, show that there is no triangle for which this is true. And so we're not going to know in advance what result to expect. But this is one of the other possibilities when we're given two sides and one angle, where we have a side angle combination that are opposite, but we've got to use the law of sines to calculate an angle. Then remember, we have three possibilities. There's a unique solution, there's no solution, or there's actually two triangles that satisfy those conditions, so two solutions. And in advance, we don't know which is which necessarily. Now, in this case, stop and look at this information. Okay, stop and look at this information. It's just something to consider. Angle A is 85 degrees. Side A is 15 units. Now side B is 25 units. And so angle B has to be bigger than angle A. And so to be bigger than angle A, it's certainly got to be an obtuse angle, doesn't it? In fact, maybe pretty big obtuse. Well, let me show you what's going to happen, and tell you that we're not going to recognize this in practice. We're going to have to see what happens that gives us the hint. So here's the idea. I have an angle A that is 85 degrees. It's almost a right angle, but you can see a little slight tilt to it. Okay, a little slight tilt to it. Okay, and I'm making this the horizontal, so the right angle would be out here someplace. And the side opposite A is 15. Okay, now angle B we'll just assume is over here someplace, because I'm going to call this side B, so angle B would be over here. Well, side B is 25 units, side A is 15 units, and this is pretty much in scale. And notice then, if this is so long and this angle is so great, there's no way that this side can reach this horizontal. If we have anything less, the angle wouldn't be 85 degrees. So the vertex of the triangle has to be somewhere along this horizontal, and it's not going to reach it, is it? And that's because of the relationship of these three pieces. Not possible. Well, how do we know that without going through a great deal of trouble trying to create a triangle that has these components? Well, here's how we do it. Here's what's going to happen. As we look at what we have is an angle and a side opposite that angle. That reeks of using the law of sines. We have one more side, side B, and so it's this relationship that I'm going to use, but I'm looking for an angle. So I decide to use the reciprocal version of that law of sines. I'm looking for angle B, okay? I know angle A, I know side A, I know side B. And so I simply put the information in. I know angle A is 85 degrees, side A is 15. I'm looking for angle B, but I know side B is 25. And after I get that information in there, then I just solve for the sine of B. That is, I multiply both sides by 25. So the sine of B is 25 times the fraction sine of 85 degrees over 15. And when I do that, then I find that the sine of B is 1.66. Now, if I try, let's look at this. Okay. If I got my calculator out now and said, okay, well, B is the inverse sine of 1.66. So I'm looking for B. I'm going to use the inverse sine function, and I'm going to calculate the inverse sine of 1.66. Close parenthesis, enter, and it says error domain. It's an error domain, which means that the 1.66 that I put in, let's just say quit here. The 1.66 that I put in is not in the domain of the inverse sine. But more importantly here, it gives us a hint that we need to look at something a little more carefully. Remember, the sine of an angle always has to be between -1 and +1. The sine of an angle can never be bigger than 1. And what we have here is our calculation told us the sine of B was 1.66. That's bigger than 1. That can't happen. And so since we can't have sine of an angle bigger than 1, then that means we have to conclude that there is no angle B for which we can take the sine of and get 1.66, which means there's no angle B that satisfies the conditions that we have here. So that's how we would find out that there is no solution, or there is no triangle that has these three conditions satisfied. Well, that's pretty interesting, isn't it? Well, in the next page, we'll see the possibility, or we'll see the example where, remember, what we've done so far is we've found exactly, using law of sines to find an angle, we found a triangle, one solution, a single triangle. We've just now found a no solution, no triangle, when we tried to find the an angle using the law of sines. And the next case is that we actually have two solutions, two triangles. Well, again, in advance, we don't know. Okay, in advance, we don't know that there's going to be two solutions. But here's what we do know. We've got a triangle that has an angle A of 20.5 degrees and a side that is opposite that of 12 meters. And then we have a second side that's 31 meters. Now, here's the scenario. This seems like we'd use a law of sines, doesn't it? Because we have an angle and a side opposite it. We have another side. We ought to be able to find the angle B by using the law of sines. What we do know is the angle B is bigger than the angle A. And remember, a triangle could have no obtuse angles. Okay, so B might be an acute angle, but we could also have a triangle that has one obtuse angle, only one. And so since we know angle B is bigger than angle A, I suppose it could be, because angle A is 20.5 degrees, so angle B could be an acute angle if it's just bigger than 20 degrees, or it could be an obtuse angle. And that's where the rub lies. That's where the issue is. So let's begin to think about how we're going to deal with this. Okay. Well, I'm going to use the law of sines to calculate the angle B. I'm going to first determine the value of the sine of B. So I know side A, I know angle A, I know side B, I'm looking for angle B. And so I actually used sine of A over A is equal to sine of B over B. And I multiplied by the denominator B, and so I end up with this expression. Okay, I didn't show it here, but that's what I've done. Whoops. So you ought to be pretty used to the idea of the things that we're doing so far. Now, what do we need? I guess I should have said this earlier. We need angle B, and that's the first thing we're going to find, and we need angle C, and then we need side C. Okay, so going through the gyrations, and you can figure this out, get out a little piece of note paper and look at the reciprocal version of this and see why I came up with this expression. And so I've just plugged my values in. Remember, B is 31, side B, angle A is 20.5 degrees, and side A is 12 units, 12 meters. And I did the calculation, I got 0.9047. Now, here's the rough part, okay, that we need to be aware of this. And here's the situation. Whoops. That there are actually two angles. All we know is that our angle B is bigger than 20.5 degrees. So it could be anywhere between 20 degrees and 180 degrees, or 21 degrees and 180 degrees. And in fact, there are two angles between 0 and 180 degrees whose sine is 0.9047. And let me remind you of that, okay? See, let's just, as an illustration, let's assume that this is the y value of 0.9047. It might be a little higher, but let's just assume this is the y value. Well, there's an angle here. See, if we look at this y value, well, this point's on the unit circle that has that y value, and this point's on the unit circle that has that y value. And so we have an angle right here that would have a sine of this y value. And we have an angle here that I called beta that would have a sine of this y value, okay? This y value. And so both of these would have a sine value of 0.9047. Now, the next issue, though, is when we go about using the inverse sine key, see, we'd say, oh, B is the inverse sine of, oh, I got ahead of myself, okay? Act like you don't see that. To find B, we'd say, oh, B is the inverse sine of 0.9047. Now, notice I didn't call it B here. I called it alpha. And because here's the issue. The inverse sine function only gives us results that are between negative 90 degrees and positive 90 degrees. And so it doesn't even think about this possibility over here. So it calculates this angle that is an acute angle. That's what it did. And so 64.8 degrees is what we would think B is. Now, we got to remember that B could be an obtuse angle. So B might be this other angle over here. And what is this other angle? Well, this other angle is symmetric to the angle we have here. So think of, this is alpha, think of this as being 64.8 degrees right down here. And if this is 64.8 degrees, take the 180 degrees and subtract 64.8 degrees, and it will put us at this angle. That would be the angle beta. Okay, so B could be 180 degrees minus 64.8 degrees, which is 115.2 degrees. And now, just verify this. I mean, you don't need to do this, but I'm going to show it. Notice, of course, that we calculated 64.8 degrees by using the inverse sine function. Okay, inverse sine of 0.9047. That's where we came up with that. I came up with that 64.8 degrees. I rounded it to tenths of degrees. Now, because I rounded it, I'm not going to be exact, but notice this. If I take this, that's the whole point. If I take the sine of 64.8 degrees, and I happen to know that I'm in degree measure mode, okay, I get 0.9048. So my rounding caused me a little bit of error here, but it's certainly close to 0.9047, isn't it? On the other hand, if I take the sine of 115.2 degrees, then I get exactly the same value. That's the point that I'm trying to make. This is where the y value of 0.9047 is. And there's two angles that have that sine value. Okay, there's two different angles that have that sine value. So that is the ambiguity here. Okay, so let's consider, well, what if B is 64.8 degrees? Okay, well, if B is 64.8 degrees, now remember, we're trying to come up with, we're trying to come up with B, angle C, and side C. We already know angle A and side B. So if angle B is 64.8 degrees, then angle C is 180 degrees minus our A minus our B, and that's 94.7 degrees. So if B is 64.8 degrees, angle C is 94.7 degrees. We have no obtuse angles in this case. Now, how would I calculate side C? Well, side C, I could use the law of sines again. Side C over sine of angle C is equal to side A over sine of angle A. And so side C is A over sine A times sine C. That's all I've done here. And I know side A is 12, angle A is 20.5 degrees, and I know that angle C is approximately 94.7. So when I put this into my calculator, I get side C is 34.2 meters. Now, let me just show you what we've got here, okay? Notice a little dashed line I put here. Here's angle A. Here's side B. Here's side A. And we've calculated angle B to be 64, we assumed 64.8 degrees. And we calculated then that angle C right here was 94.7, and the side C is 34.2, which is the largest of the sides because C is the largest of the angles. Now, let's consider what would happen if B was 115 degrees, okay? Well, if B was 115 degrees, angle C would be 180 minus angle A minus angle B. And in this case, we would get angle C is 44.3 degrees. Now, I would use the same calculation to determine side C. Okay, I'd use the same calculation. I know A, side A, angle A. Now I know angle C. And so I put those values in so I can calculate side C. And this time I get side C is 23.9 meters. Now, notice that's the reason that you saw this little dashed line in here. If angle B, see, I mean, I still have to have this side B, don't I? So in this case, I've got side B is here, but since angle C is obtuse, side A is coming over here. In this case, I've got side B, the same place, but angle C is acute, and so this side A is actually coming this direction. But the angle B that is here is 115.2 degrees. That was the assumption I was making based on the two possibilities. And we, of course, calculated angle C being the 44.3 degrees, and we found out that side C, which is this side, is 23.9, which is in the middle, isn't it? Okay, it's in the middle, not the largest, because this is the middle angle, 44.3 degrees. Well, so we have to be a bit careful. And just a reminder that we needed to complete our job, we needed to find B. We had two possibilities for B. We needed to find C, angle C, and so we found angle C that goes with this B, and we found side C that goes with this angle B. And likewise, we did the same thing over here. So we have two completely different triangles that have the information satisfied, where angle A is 20.5 degrees, side A is 12, and side B is 31. Two different triangles that satisfy that information. Now, again, we didn't know that, but we have to be on our toes that there is the possibility for a acute angle or an obtuse angle, and the inverse sine is not going to find the obtuse angle. So we have to keep on our toes about that. Well, that ends my discussion about the law of sines generally, but specifically the ambiguous case of the law of sines, which once again is where we're having to use the law of sines to find the measure of an angle as opposed to the measure of a side. When we're using the law of sines to find the measure of a side, we already know both angles, and so we don't run into trouble then. Signing off.